All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor James Anderson, who is an assistant professor in the Department of Electrical Engineering at Columbia University, where he's also a member of the Data Science Institute. So, brief bio of James. He holds a Bachelor's of Science and Master's of Science in Systems Engineering from the University of Reading. He then got his PhD from Oxford, and then spent some time at Oxford as a junior researcher, and then he was a postdoctoral scholar in the Department of Computing and Mathematical Sciences at Caltech. His research generally spans the intersections of optimal control and machine learning, focusing on multi-agent systems, cyber-physical systems, and power grids and high renewable energy in particular. Today's talk is dedicated to collaborative learning for control of heterogeneous systems. I personally really enjoy his work, and I'm very excited to hear more about it today. And therefore, I'm very happy to give him the stage. Go ahead, without further ado.
Thank you very much for the very kind introduction. And yeah, I just wanted to say this is a wonderful initiative. There are some really fantastic talks online, so I'm really happy to be here. So I'm going to talk today about some recent work on collaborative control, specifically federated learning and meta-learning, and talk about how we can actually apply this in a control setting where we care about things that typically sort of the machine learning purists don't care about, like dynamical systems, stability, and performance in some sense. So this work has been done by mostly by three of my students, Han, Leonardo, and Donglin, as well as collaboration with Aritra Mitra at NC State. So kind of the theme of the talk is, there's this idea that collaboration should always benefit you. But anyone who's ever been in, an undergrad lab knows that when, you start work and then 20 minutes after the lab starts, a student walks in late, clearly they haven't done any preparation and they get assigned to your team, it's not going to be necessarily a beneficial collaboration, at least not for you. So something I'd like to tease out from this collaborative learning work is, given the diversity of people willing to participate in a task, who may have slightly different objectives, and certainly they have their own intentions and way of working, when is it actually advantageous to collaborate? And in what way does this collaboration impact the final outcome? And we're going to look at this through the lens of some very simple control problems, and through sort of, again, very basic learning algorithms. And so part of the motivation behind this, at least the federated learning part of this, is a very simple example, perhaps the canonical example. Imagine you have multiple, let's say, hospitals. Each hospital serves its own population. It may be sort of very geographically remote from the other hospitals, and they obviously collect patient data. Now, it would be great if they could pool this patient data together to build a predictive model of a particular illness. And the problem with this is that medical data, for example, you can't just go around sharing it. There are privacy concerns. And so but we would still like this model that captures the data from a diverse population. More data is generally better. And the idea that these hospitals are in different geographic regions means you're getting a slightly richer data pool. So how do you go about building a model that captures all of this data if you're not actually allowed to exchange the data? Well, this is where federated learning comes in, and the idea is really simple. And each, I'm going to call it agent, but hospital, is allowed to train a model on their own data. And now, while you're not allowed to while you're not allowed to share data, you are allowed to share models. And so if everyone builds their own model, and for the sake of simplicity, let's say you all agree on the same number of, weights in your neural network and layers, then perhaps you can exchange or average these neural network models. And you do that, And then the average model is sent back to each hospital or data center. And another round of learning proceeds. And now, except this time, you're seeded from this common model. And the process repeats. And hopefully, after enough iterations, you end up with a model that sort of indirectly covers the data from the different hospitals, despite the fact that the data was never actually shared. And if you think beyond sort of hospital data to other settings, I'll give you an example later. Typically, there may be thousands or tens of thousands of users, in this case, hospitals. And it's just, there are other reasons why you wouldn't want to share the data. Like, it's not very efficient to share data all the time. If the model is sort of smaller in some sense than the data set, then sharing the model is going to help with communication efficiency. And the second part of the talk, which kind of builds on this federated idea, is task adaptability. So imagine I have a distribution of tasks. In this case, these are drones, and the task will be to, I don't know, track a certain path. And each task is comprised of a different drone, and the drone operates in a different environment. And so from all possible distributions, I would like to sample a few, a finite set. I would like to, first of all, learn a controller based purely on the training data from the tasks I've sampled. I'd like to learn a policy that's going to do well on all of these subsamples. And then more importantly, I would like this controller to be easily adaptable to any other task in the distribution, even if that wasn't included in my training set. Okay, which you can think of that as taking a foundation model and then trying to fine tune it for another task. And in the context of control, we would like to ensure things like stability is preserved, some sense of optimality maybe. And so that's going to be the
James,
second part.
Quick question,
Yes.
sorry, I don't want to cut you off, but there is a question in the chat from Subrata asking whether, first of all, the agents spread across the same geography, or do they have the same workspace?
No, completely in their own environment. Imagine I have a lab where I'm running some drones, you have a lab where you're running some drones, and someone else. So absolutely can be completely different geography. The drones can be different as well. I mean, there needs to be, I'll get to exactly how similar or dissimilar they need to be. And obviously, if they're completely different, this isn't going to work. But we'll actually tease out specifically what we need in terms of similarity as we go through the talk.
Great, thank you very much.
Great question, and please keep them coming. Okay, so the outline of the talk is going to be, first of all, I'm going to give you a slightly more detailed intro to federated learning. And then I'm going to set up the model-free learning problem for the specific control problem we're interested in. And then I'm going to specialize it to the collaborative learning problems. So, okay, federated learning in a few slides. It takes a client-server model of computation. And so you can imagine the situation where you have lots and lots of clients. The clients all have differing computational capability. They all have their own data. So the volume of data may be different at different clients. The data may follow different distributions. The only thing that's sort of assumed is that the clients can compute reasonably efficiently, and that the bottleneck is actually communication, not computation. So as I mentioned previously, each client is going to compute its own model. It's then going to send this model to the server. The server is going to perform some sort of statistical aggregation. It's then going to broadcast the aggregated model to every client, and the client is then going to recompute a model. And one of the first applications for this was actually Google using this for predictive text. And in this case, there were probably, I think there were thousands of clients in every round. So let's take a step back and look at the centralized learning. I'm using learning very, very loosely here. But if I have some data, then typically it's all in one place, or at least globally accessible. And let's say I'd like to do a simple linear regression. Okay, then great. I'll run least squares. I'll get my gradient and my offset. and all is good. In the federated setting now, we'll imagine we've got 3 clients. They have their own data sets. And so what will happen is locally, they will compute their own gradient and bias. They will submit these to the server. The server could just take an average, send those averages back. They'll start relearning. And if after a large number of iterations, you'll see that these should sort of hopefully align and you get an estimate. Now, this cartoon is obviously massively overplaying how well that fit would happen. But if there were, slightly fewer points in the red data set, then there would be a sufficient weighting that the line here is actually going to be the federated average model. So to make this slightly more technical, we can formulate this as a stochastic optimization problem, where the parameter x, this is going to be our vector of parameters, and we would like to minimize the population risk, where we have some loss function, which is a function of our model parameters and some random variable zeta. So our goal is to pick x to minimize this function. The catch is that zeta is drawn from a probability distribution which we don't know. And we also, it's not quite as centralized as this objective looks. We actually have n clients, where each client generates m samples. It doesn't need to be the same number of samples for each client, but for simplicity, let's say it is. And we denote these samples as d sup I. Then we can rewrite our problem as minimizing x subject to, or 1 over the number of clients that we have, n, times the sum over fi, where fi is now the loss function applied to the specific distribution of the tasks. So what we're actually doing now is going to minimize the empirical risk. And, if hopefully the empirical risk is going to be close to the population risk. But the point is, solving these subproblems is done completely independently. So let me give you the sort of prototypical federated learning algorithm, fed average. Now, I'm not advocating that you should actually use this algorithm, but it serves the purpose of setting up the model of computation that we're going to be using. So the input to this algorithm is going to be the number of periods that I'm going to run the algorithm for. So this is the number of outer iterations. Tour is going to be the number of steps of the local optimizer I'm going to run, and the step size that I'm going to apply at my learning rate, essentially. So the first thing that happens is the server selects a subset of all of the clients. So we don't need every client to participate. And it's going to broadcast some initial model, xk, to all the clients in the subset that are chosen. Okay, so each client, and this is done in parallel, is going to set this xk as its starting point. And then it's going to run tour minus 1 iterations of essentially whatever optimization algorithm it wants to run. So for simplicity, let's just say it's going to run stochastic gradient descent. Okay, so it's going to fix a data point eta. It's going to compute a stochastic gradient, and then it's going to update its local model. And it's going to iterate around this for tour minus 1 iterations. Once that's finished, it's then going to send the difference between what it just computed and the former global model. And this delta is what's going to be sent to the server. And then the server is just going to take an average over all of the updates it's received from all of the clients. And it's going to it's then going to update the original global model xk via this average. And this xk plus 1 then gets broadcast back to the clients. And we repeat this for k minus 1 iterations. So what you see here is all the training is done locally by each client. No data changes hands. And the server is doing the aggregation. And the hope is that xk plus 1, or x at big K minus 1 after the final number of iterations has produced a good model that is representative of all the client's models. So this is sort of the prototypical template. You can change whatever iterations you do in here. You do that, you change the name of the algorithm. Okay, you can do things like proximal methods, insert whatever splitting methods, whatever you want to do, you put in here, you substitute that in here, and you get a new federated learning algorithm. And of course, then it's up to you to prove convergence and all the other technical parts. So this algorithm, we're going to come back to this algorithm and look at how this is, what this looks like for certain control problems. But this is very much the thing to keep in mind. So okay, let's get to the control setup, and this is, again, we're choosing the simplest possible control example. This is linear quadratic control in discrete time. So we have a simple update equation. X now is our state. Okay, this is going to be, like for drones, a vector of positions, velocities, relative distances, for example. And U is going to be our input function. And we're going to look at this over a finite time horizon. And we're going to assume that the initial condition is unknown, but for reasons that will become clear later, we're going to assume that the expected value of the initial condition is 0, and that the expected value of the first moment of the initial condition is positive semi-definite. And our objective, so it's well known that this problem admits an optimal controller that is both linear, just a matrix, and static. It doesn't change in time. And so we're going to enforce that we would like to find such a controller K. Our policy is going to be our input at time t is equal to minus some matrix K times the state at time t. And K needs to stabilize the system. Okay, so the magnitude of the largest eigenvalue of the closed loop dynamics, so that is these dynamics when I plug in U is equal to minus Kx, needs to be less than 1. So that just ensures that x of t will go to 0 as time goes to infinity. And I should say that this, important to note that this set K is actually non-convex, and that's going to be problematic. And the quadratic cost we would like to minimize, so we like to choose this K so that we minimize this function where Q and R are positive definite matrices, and Q is essentially a weight on how much we want to penalize X drifting away from 0. And R is a weight that is going to penalize applying large inputs. So our goal is to choose a K that minimizes this quadratic cost, subject to being stable and respecting the dynamics of the system. So we can rewrite this in this way. And the classical solution, it looks a bit odd the first time you see it, but essentially, if we can solve this matrix equation called the discrete algebraic Riccati equation for a positive definite solution pk, okay, and this all you really need to see is this is a nonlinear function of the thing we're trying to solve for, and our problem matrices A, B, Q, and R appear in it. If I can solve this for pk, then the optimal controller is given by this algebraic expression, and I'm using star to denote optimal solution. Okay, so again, the thing to take away from here is that the optimal controller is a function of all my data matrices. So the question really is, how do we compute this? And we haven't got to the collaborative setting yet. This is just background. How do I compute an optimal controller when I don't actually have knowledge of the model and the model parameters? So something we could try is, well, let's just set this up as an optimization problem. And to begin with, let's assume we do have access to the problems. Obviously, trying to solve the Riccati equation and then this K without the parameters is going to be problematic, but maybe we can do something clever if we just set up a gradient descent type algorithm. Right, so our optimization variable is the controller K. Let's just apply gradient descent. So our updated K is going to take the initial value of K. There'll be some step size, and as long as we've got a gradient, then we can compute this update. And if we're lucky, this update might converge to something useful. So the analysis that follows really comes from this paper by Mariam Fazal and collaborators in 2018, and it's going to be the framework that we're going to apply. And she was able to show a few really useful and amazing properties. So first of all, I'm going to rewrite my LQR problem objective just as this quadratic form, right? So my initial conditions, pk, which I don't have. The point here is the matrix P is a function of k. And I can rewrite things so that pk must solve this Lyapunov equation. So my reformulated problem is to minimize this quadratic subject to dynamics and stability constraints. And this is a very non-convex problem, right? Because pk is a horrible function of our variable k. My stability constraint is defined over a non-convex set. And so as long as n is greater than or equal to 3, there are plenty of problem instances where this is going to run into trouble. But let's just see how far we can get with this. And so the reason for writing the objective function in this form is it makes it easy to write down an analytic gradient. Okay, so this is given here. It looks a mess. The point here is really that you can write down this gradient, and it takes the following form. And the only thing to note here really is that this sigma k matrix is, if I were to fix any controller k, and then x of t is going to be my closed loop dynamics. So x of t plus 1 equals a minus bk for some choice of k times x of t, then it's the expected value over this outer product summed over time. Now, this isn't particularly useful on its own in the model free setting, because again, we haven't got rid of the fact that we need r, b, p, a, and all the parameters. But for analysis, it's super useful. So what Fazell was able to show was, we can take a slight sidestep here, but a function f is said to be gradient dominated if the following condition holds. And if I take the gradient of my function f at some point x, then there exists a constant mu that upper bounds the difference between the value of f at the point I'm at and the global optimal. So the way to interpret this is, if the gradient of f of x is small, then the distance between x and the optimal point is also going to be small. And so if f happens to be smooth, then this result tells us that a gradient dominated function, if I run gradient descent, I will get linear convergence to the optimal point, even if the function is non-convex. And so what Mariam Fazell and a team were able to show is actually the LQR problem is gradient dominated. So if I choose any k such that my objective function is bounded, then the gradient dominance condition holds. And she even isolated the parameters that make up this mu parameter. Okay, and so they are problem data parameters, right? It's the minimum singular value of the cost matrix R, the minimum singular value of this closed loop covariance matrix, and then actually the optimal closed loop covariance matrix. And so what this tells us is, if the gradient is equal to 0, then k is actually an optimal solution. Or it's possible that sigma k is not full rank, but the way we're choosing our initial conditions actually rules out this condition. She further showed that actually the LQR landscape is almost smooth. So what that tells us is that if we run something like gradient descent for a sufficiently large number of iterations, then the controller after n iterations is going to be within epsilon of the optimal controller. And you can run other descent algorithms such as natural policy gradient or Gauss-Newton. We're only going to focus on the simplest one, gradient descent, and it'll be clear on the next slide why. So in order to run any of these methods, you need access to at least the gradient, possibly the covariance, and possibly other model parameters. And so if you don't have access to the model, you still can't do this. So model-free control is nothing more than saying, okay, well, instead of working with the gradient, we're going to work with an estimate of the gradient. So the problem now is all about, how do I estimate the gradient of my problem for a given choice of controller? And can I come up with an estimate that is good enough such that this sequence is going to converge? Now, you could look at natural policy gradient and Gauss-Newton, but then you would need estimates for other parts of the model. And you can do that, but for simplicity, we're not going to. So the model setup is we don't have access to A, B, Q, and R, but we do have access to a closed loop simulation. So what that means is we get to choose a K, and we get access to input and state measurement from time t equals 0 to time t equals L, assuming we played some controller K. So we just get trajectory information. And the idea is that we should be able to use this simulation data to construct a gradient estimate, grad C, for my choice of K. And we're going to plug this into gradient descent. And if we've done a good job here, then we're going to get, hopefully, an optimal controller out of this. So this is actually a pretty well-studied problem. One way of doing this, this is a one-point gradient estimate. There are two-point, multi-point estimates, but this is the simplest, is we're going to draw n random matrices. So it's going to be S equals 1 to n. And the Frobenius norm is going to equal some parameter, small parameter r. And then our gradient estimate is going to be 1 over n. So we're going to average over. And now this summation, so inside the summation, this is one simulation run initiated from x0, from our allowable distribution, where the controller is some initial controller plus our perturbation. And then we multiply this by the number of states, the number of inputs, and our smoothing radius r squared, and we average. And this actually gives us a bias estimate of the gradient of C of K. Now, this isn't the best estimate. You can do better using 2 points, but it's kind of efficient. So this is our estimate, and the only thing we really need is access to this simulation in order to produce this. Okay, so hopefully if we choose, sorry, I'm switching notation now, but if we do take sufficiently large number of steps, then with high probability, we're going to get a controller after the kth iteration that is epsilon suboptimal. And Fazal and lots of other people now have extended this work, but essentially you get a polynomial computational and sample complexity bound. So the work of Malik and Martin Wainwright did a really thorough analysis on different LQR problems with different gradient approximation schemes. This was also extended to continuous time by Mihailo Jovanović's group. And recently on the archive, there was a nice paper looking at how you can actually improve the sample complexity from a 1-point estimate. Ideally, you'd use a 2-point estimate, but I'm going to skip that today. So, okay, so now we've got enough in place to consider the federated learning setup. So this is joint work with Han, Leo, and Aritra. So the motivation here, again, think back to the drone example. Maybe I've got some drones in my lab, a collaborator has some drones in their lab, a third collaborator has some drones in their lab, and we would like to get we'd like to work together. We'd like to design a controller that is going to work well on each of our drone setups without having to retrain from scratch or rebuild a controller. So we're going to assume that we have capital M dynamical systems. Okay, and they take exactly the same form as before, and we're just going to denote the ith system dynamic with this parentheses I. Everything else is exactly the same. And our goal now is to construct a common controller K that has to work with each of our M dynamical systems. So it needs to stabilize each of the systems, and ideally, we would like it to minimize this quadratic function. Okay, so this function, we now have M of them, denoted Ci. And the thing to note is they share the same quadratic cost, Q and R, positive definite matrices. But our overall cost now is the average over this, subject to the fact that our common controller stabilizes each system and respects the dynamics of each system. And we're going to make the assumption that AI, BI is stabilizable. Okay, so this kind of looks like it's similar to an H2 problem or robust H2 problem, but it's actually a little bit different. I'm not going to go into the details specifically as to why, but this isn't a non-standard control problem. And so the questions and challenges are, first of all, is it even possible to get a common policy to stabilize all systems in the model-free setting? And if so, under what conditions? If we do manage to learn a common policy, how close is it to each agent's local policy? Maybe it gives terrible performance. And what is the sample complexity? Is there actually any benefit to the individual agent for participating? And then later on, we'll look at how can this optimal controller then be fine-tuned on unseen systems. So that'll be the meta-learning part of the talk later. So to get towards the first part of the question, the systems that we consider can't be completely arbitrary, right? If you have a model of a bus and a submarine, there's no real hope that there's going to be some sense of a common controller is going to be able to stabilize both of those systems. So we define two parameters, epsilon A and epsilon B, and it's essentially the largest difference between any two A and B matrices across our M systems. Now, you don't need to know epsilon A and epsilon B ahead of time, but epsilon A and B are going to appear in the performance bounds. So if you wanted to link this to classical control, you may have some nominal system G0. And the idea is to design your controller K such that it actually stabilizes and provides performance to all systems that are sort of suitably close. And typically this is modeled by some sort of perturbation. And what our heterogeneity constraint is saying is that the distance between worst case problems can't be arbitrarily far away. It needs to be bounded. And we're actually going to define a low heterogeneity regime. And the reason this is necessary is because if we just take this very, very simple scalar two-system example, where the dynamics between the two systems are exactly the same, there's some alpha parameter in the first system and minus alpha in the second, the B matrices would be the same. And we'd like to find a common controller here. Then in this case, our epsilon A parameter is 2 alpha and epsilon B is 0. So there's no heterogeneity in the B matrices. But if this epsilon A is greater than 2, then this means alpha is greater than 1. So both of these systems are unstable, open loop. And so the stability requirement would be we would need the magnitude of alpha minus k to be simultaneously less than 1 and alpha plus k less than 1. And this can't happen. So there's no stabilizing controller. Right? So federated learning is never going to work in this setting. So the take-home message here is that we really do need to bound, in some sense, the heterogeneity in these systems in order for this framework to apply. We can't just take arbitrarily different systems. The other quick thing I'd like to say is that this isn't necessarily a good metric in terms of system similarity. Any system engineer will look at these metrics and you can build, or, quickly write down these two subsystems. And according to our metric, these systems are similar, but in reality, they're structurally very different, right? The system on the left is stable, the system on the right is unstable, yet epsilon A is going to be very small. The system on the right is going to be very difficult to control. The system on the left is going to be easier to control, yet epsilon B is going to be relatively small. So this, I'm not claiming this is a great metric for quantifying heterogeneity, but it works reasonably well. And here are some possible fixes. I think this is actually a great project for someone to take a look at. So let's port over our federated LQR problem to the Fed average prototypical algorithm. Okay, so, and you'll see these things look very, very similar. Apart from the fact that I've, just to confuse you all, I've changed notation slightly. So there's going to be n-1 outer operations. Okay, and the first thing that's going to happen is the server is going to broadcast a controller to all the clients. Now, there is an implicit assumption that the initial controller does actually stabilize all the clients. And I admit that is a large assumption. It's actually, there's plenty of work that has looked at getting rid of it, and we have some forthcoming work that shows how you can do it in a sample efficient manner. But for now, just assume you have a controller that stabilizes each system, and it's broadcast to every client. Okay, so every client sets this K as its initiating point. And we've predefined the number of local loops each client is going to run. The first thing it's going to do is it's going to take the initial controller and it's going to estimate the gradient, right? So it's going to run our 0th order algorithm. So what that means is it's going to run a simulation. The length of the simulation is going to be Tor time steps. You're going to pre-specify the smoothing radius R, and the input is the controller, and it's going to spit out this estimate C hat, or nabla C hat, gradient C hat. We're then going to take this estimate and we're going to put it into a gradient descent update. Again, you could do something more complicated here. We're just going to look at simple policy iteration via gradient descent. And then finally, the client looks at the difference between the global model and what it just computed by running the update policy. And it's going to send this delta to the server. And each client is going to do this completely on its own. No data, no trajectory data is shared. Nothing is shared client to client. And the server is going to average these updates. There are also local step sizes, which are tunable parameters, which I'll get to later. It's going to take this average, it's going to add it to the existing controller, and this becomes the controller for another round of local updates. And so we're going to do this n-1 times. So before getting to the model-free case, what happens if you actually do have access to the problem matrices AI, BI, and the cost? Well, in this case, we can write down the explicit update. It's nothing more than, so this constant term, these are the inner and outer learning rates. M is the number of clients. And you sum over this, all of the gradients that are estimated. And remember, we know, I'm not writing it down because it's kind of messy, but we can write down this term. Okay, so pretending we have everything, then essentially the intuition says that if epsilon A and epsilon B, so the heterogeneity, if the similars are similar enough, then the gradients, the policy gradients, right, that is the gradient of each Ci, Cj, should be close to each other. And actually we're able to show that if you take any two agents and you have the model, then the difference in norm between the gradient of the ith agent and the jth agent is actually bounded by some linear function of how different the A matrices are and how different the B matrices are. This H1 and H2 of K, we can write down explicit formulae for these. They're kind of messy, but essentially they are polynomials of the problem data. And so they're things like the minimum singular value of R. The only thing that changes is they do change with every choice of K, but everything else, all the other factors in these polynomials, and they're typically fourth order, they're reasonably well behaved. We can write these down. They're in the paper. But essentially what we have is that the gradient difference between I and J is of order of the magnitude of how different these systems are. And so another interpretation of this is that the gradient of agent I can be well approximated by the gradient of agent J. And this is why when you look at this term, you'll see that actually this update equation is going to converge. So examining this a bit further, this is precisely the bound that I wrote on the first page. So assuming that the controller K that we've chosen lives in, and it needs, remember, the controller K needs to stabilize system 1, 2, 3 up to M. So for a 3-system example, if these lines represent the stabilizing sets, which remember are all non-convex for system 1, 2, and 3, then we need to choose a controller that lives in the intersection of these sets. Then as long as we're somewhere on, as long as this line is somewhere in that set, then for any choice of central controller K, what that tells us is the gradient of K, if we were to apply an update step, doesn't take us too far away from where we started. In fact, we're not going to leave this ball where the radius of the ball centered at the K we're at is of radius on the order of the magnitude of the heterogeneity. The second part of the result tells us that provided, after n rounds of running this algorithm, provided that the heterogeneity, so epsilon A and epsilon B, satisfies this requirement, then we get a per iteration performance guarantee. Right? And again, G1 and G2, these are polynomials that we can write down, G3 too. And what this tells us is that after n iterations, the gap between the controller Kn and the optimal controller for every task is bounded by this following equation, which looks kind of ugly. But it's, so this first term, this is actually a contraction term, so don't worry about what's in here. The point is that this is less than 1, and this is raised to the power n, where n is the nth iteration of the algorithm. So this gets smaller as n increases. And so this reduces the initial optimality gap. So you see this all the time in standard convergence analysis of an optimization algorithm. So this term is getting smaller with n. And typically, you'd like to see this thing go to 0. But the price we pay for the fact that systems are different, so this optimality cost, induces this bias term. And this bias is a function, again, of a ball of radius, is a function of the system heterogeneity. The other thing I'd like to point out is that after any number of iterations, our controller Kn from the algorithm is stabilizing for every system. Okay, so what we've got is this is the standard convergence rate, and we're paying this price for working with different systems. So if I go back to my original picture, what this actually tells us is provided we choose an initializing, stabilizing controller for all our subsystems, we never leave this destabilizing region. And moreover, at every point, we are within a ball of epsilon radius along here, and the optimal controllers for each of the subtasks live inside this region. Okay, and we're going to be, after n iterations, we're going to be this close to each of those optimal controllers. So yeah, to summarize the final bit, the difference between the optimal controller and the from the algorithm, had we run this for an infinite number of iterations, and the local optimal is of the order heterogeneity squared. So moving through to the model free case, all of our results go through exactly, they look exactly the same. Some of the parameters change slightly, but the constants. And the reason is because with our 0th order estimation, provided we choose enough, we run enough, get enough trajectories, and the horizon length is long enough, and the sampling radius is small enough, then with high probability, our gradient estimate, the difference between our gradient estimate and the true gradient estimate is small. And the point here is that this error term, this error, is reduced by 1 over ML, where M is the number of agents. Right? So as I increase M, introduce more agents into the problem, this actually gets smaller with high probability. Okay, so this variance reduction is what allows us to show that the model-free version is going to converge. So again, informally, what this means is each individual agent, provided they participate, gets a 1/ml speed up per iteration relative to the case where they didn't collaborate. Okay, so they actually get the benefit of collaboration kicks in here. All other results in terms of convergence and staying and stabilizing controllers from the model free case run through. The overall sample complexity is improved by a factor of 1 over the number of agents. So again, more agents means improved sample complexity. And this was an open question actually as to whether or not you could achieve this. It was sort of hoped for and hinted at, but it certainly wasn't proven. And each agent's sample cost, in order to get an epsilon suboptimal solution, improves from 1 over epsilon squared, where this is the suboptimality, to 1 over m epsilon squared. Okay, so everyone benefits, provided the system satisfy this small heterogeneity criterion. So I can show you some simple simulations. So this was a system with 3 states and 3 inputs. The heterogeneity was in A and B was set to 1/2, and our simulation engine took just 5 trajectories, a horizon length of 15 and a smoothing radius of 0.1. And what you can see here is the benefit of having multiple agents participate, right? So the red curve is showing after n outer iterations what the error is between the optimal controller for the first task and the optimal cost function after n iterations. And you see effectively as you increase the number of systems, this error decreases more quickly and gets to a lower error value. You can also look now at fixing the number of systems and looking at how the changes in heterogeneity play a role. And they do exactly as you would assume, right? As you increase the heterogeneity, the error increases. Okay, so this is just a sort of proof of concept, or sorry, proof of theory that this thing is actually working. So I think I've just about the time to get to my final part of the talk. And this is, can we now take our globally optimal controller or our global controller KN, which you can think of as a foundation controller, if you like, and apply it to an unseen system, right? So an AI and a BI that wasn't part of the original set. And A, is it going to stabilize that system? And B, can we fine tune? And by fine tune, I mean, if we run a few local iterations of, say, stochastic gradient descent, can we get some sort of guaranteed performance on it? So the details of this paper, this is now with Leo and Han and another of my students, Dong Lin. It's appeared in L4DC this summer. And this is now a meta-learning problem. So the setup here is, imagine I have a distribution, and this is a distribution in task space, right? So if I sample a point from this task space, then what I get is a linear dynamical system, right? And maybe that's represented by these points in pink were random variables chosen by some sort of distribution. And so actually, I'm skipping some of the details here. We're going to allow each task to have its own cost, so its own Q and R matrices. So as well as points in the distribution defining a system, they're also going to define a Q and an R matrix. And what we would like to do is design a controller that effectively stabilizes. If I were to sample any point in the distribution, my controller K should stabilize and provide some sort of performance guarantee to it. And so the meta-learning setup is, well, actually, I'm going to sample, in this case, 1, 2, 3, 4, 5 systems. I'm going to learn a controller for these 5 systems. And that controller should then be easily adaptable to any other sample I draw from the distribution. So just to be a little bit more concrete, an individual task that comes from this distribution is modeled by some matrix A, B, and some cost matrix Q, and some cost matrix R. And associated to each task is an individual task objective, which is nothing more than the standard LQR cost. So meta-learning has been used typically in a supervised learning setting where you would take, in this case, the tasks might be coming from different data sources, right? Where I have a corpus of text, a bank of images, some audio files, and in our case, dynamical system data. This would be a multitask data set. And the idea is you would take this data, you would develop some foundation model, and an example of one of these things would be one of the ChatGPT or Llama models. And then what would be nice is I'm going to adapt now my foundation model so it can do something that it was not necessarily trained to do, but I want this training to be efficient, right? It shouldn't be as costly as training and learning the foundation model to begin with. And so what we're going to do is really port this over to the LQR cost, to the LQR setting. Right, so again, imagine I have a drone or a vehicle, and my cost matrices are going to sort of represent the environment. I guess we're in Australia here. I would like to design a policy that minimizes, again, this is going to be a quadratic cost. Now, I'm going to be given a bunch of different environments, right? So the different environments, I guess I'm in the North Pole, somewhere in the Amazon, and let's call that Switzerland. And in each place, I'm operating a slightly different drone, right? These aren't the same. Again, they need to be similar-ish for this to make sense, but I'm given a set of these training tasks from which I'm going to learn some controller K. Now, the question is, how well is this controller going to work, and how easy is it to adapt, when I apply it to a different drone operating in some other environment? So we're going to use the MAML algorithms. This was developed by Chelsea Finn in 2017, and it was developed in a supervised learning setting. So we have a distribution of tasks where, okay, in this case, it's a finite distribution where a specific task is drawn, and a task will have some features. The ith task, will have some a feature vector XOR and a label. So if this was image data, a label cat, dog, and I'd have a bunch of images. So we have our data set, and we would like to minimize some empirical loss, okay, to find some common model theta that is going to do well across. So my theta vector needs to do well across everything I've sampled, my M samples. And the way they set this optimization problem up is a bi-level optimization problem. This is called MAML, the model agnostic meta-learning algorithm, where my cost function, I'm going to sum over the loss functions for each task. I have the data for each task, and the model theta naught is common. Okay, but this theta naught isn't just an arbitrary model parameter. It's set up so that theta naught is actually one step of policy gradient algorithm. So what this tells you is that theta naught, if I apply this to a future cost function, is sort of one step ahead of you, right? It's one step optimized. This is actually a pretty difficult optimization problem, but there's a bunch of heuristics out there that will solve this. So we can port this over to the LQR case. So we would like to design a common controller, K-star ML, right, that can efficiently adapt to unseen tasks. And the objective, the MAML objective, is 1 over M times the sum of our individual cost functions. And this is exactly one model-free policy gradient step. Right? And again, it assumes you have access to this gradient, which you don't. And I just want to highlight, again, this is a really challenging problem because, again, we're optimizing over a non-convex set. We don't have access to the model, and we need to prove, because we have this dynamical system set up, that our controller is stabilizing and close to locally optimal controllers. So this was Mollybog and Levi studied the landscape of this problem in a slightly restricted setting and showed that in some cases it satisfies the PL condition, and in other cases it doesn't, which makes things difficult. And then Musavi and Dollerud provided the first convergence analysis where all the systems were the same. So there was no heterogeneity amongst the systems beyond like the initial conditions. And essentially this algorithm, this is our MAML algorithm, which deals with heterogeneous systems. I'm not going to get too much into the detail of it, but again, it looks very similar to both the federated learning and the MAML algorithm. Okay, so we assume that a subset of tasks T have been subsampled. We're going to run n-1 outer iterations. So now locally in parallel, each agent is going to run a gradient estimate. Now, we need to keep track of second order information here. So we need the Hessian matrix as well. So this is less sample inefficient. It's also, from an analysis point of view, is a bit more of a headache because we need to keep track of things like Hessian estimates. But there are 0th order algorithms that will do this. We can use a more complicated algorithm to produce that. But essentially, we can produce these estimates. And then locally, you update your controller based on the gradient you've just estimated. You update the Hessian based on your second order information. This information is then sent to a server where the server updates the global average and the global policy. The details, again, aren't particularly important, but again, it's very much a server-client framework. And effectively, what we're able to show in the model-free case is that every iteration, so for every n equals 0, 1 to n-1, we have a stabilizing controller. For every task, the distance between the controller the controller after n iterations for the ith agent and the ith agent's optimality is bounded by some epsilon plus a small function that is a function of how different the systems are, right? So this is going to be our epsilon A, epsilon B, except now it's including an epsilon for the Q and the R matrices. Okay, so this is our price of heterogeneity. And for all tasks, and this is, I should say, this is all tasks, not just the sample task, right? This is all tasks in the distribution. The MAML optimal controller, so this is if we were allowed to run n to infinity, the distance between the MAML optimal controller and each task's optimal controller is bounded by some well-behaved function of the heterogeneity. Okay, so what this tells us is that we are very close to not only the sub-problems optimal controller, but the unseen controller as well, right? So one step of SGD will get you, or 2 steps of SGD will actually get you to the optimal local controller. So I'm running out of time. I'm going to end with an example. So here is a nominal system. This was actually a system that modeled a Boeing aircraft that was hacked to make it unstable. So we have 2 inputs, 4 states, and some initial stabilizing controller taken from the literature. And we look at m equals 50 tasks with various heterogeneity levels. And what I'm showing on the left is, so this is on the x-axis, the number of iterations. I'm showing the gap between the optimal distance between the optimal controller for the first problem and the MAML controller applied to the first quadratic cost. And as you can see, the gradient, the error is decreasing rapidly. On the right, you can see how this changes as I increase the heterogeneity, right? As the heterogeneity I didn't actually give you the numbers, but as the heterogeneity increases, so the error increases. And just to show that this actually does work well on unseen tasks, this blue line is showing what happens if I take an unseen task and I just try and adapt it using a stabilizing controller using stochastic gradient descent. And what you can see down here are 3 completely unseen tasks that are initiated from the MAML optimal LQR controller, and you'll see that the error really decreases quite quickly after actually not that many iterations. So I think I'm probably completely out of time now, so I just want to end with a very brief summary. So we've given the sort of the first, provided the first proofs that federated learning can actually be applied to optimal control that highlight the performance benefit in terms of the heterogeneity of the agents that participate. We've derived sample complexity and computational complexity bounds, as well as proved that these things can actually stabilize the system. And then in the meta-learning case, we've shown that actually the classical MAML algorithm is something that will demonstrably give you a performance benefit in multi-agent LQR problems. And I think there's a ton of ways that these problems can be extended. We've only really sort of taken, Fed average and MAML are the 2 simplest algorithms for federated and meta-learning you can write down. I think there's a ton of work that can be done. All of these bounds can be improved using more elaborate algorithms. I think this is a fun and interesting place to be working. And if you have any questions, then please just drop me or my students an email, and we'd be happy to talk. So with that, I'm gonna end. Thank you very much.
Okay, thank you so much for Professor Anderson. Thank you so much for your great talk. And Joel has to leave early for a faculty meeting, so he asked me to say sorry to you. And there are several questions in the chat, and I can read them. So the question, one question is, can private data be leaked to another client through the global updates? Suppose we have an attacker as a client, will it be able to retrieve some private information of other clients by doing specific updates?
Right, that's a really good question. So yeah, you've in the federated learning setting, you have to be, when it was initially, years back when it was first being, when the first sort of algorithms and papers were coming out, lots of the results were claiming because the data is kept private, then this algorithm preserves privacy. But there has been a subsequent line of work that says, just sharing this gradient, the information that the clients, the difference between the previous model and the updated model, just by sharing that, if an observer was able to observe that, they could reconstruct gradients. And so these things don't have results that are as strong as, say, differential privacy. Now, there's also plenty of work that has now looked to specifically strengthen federated learning algorithms to include things like differential privacy, include adversarial agents. We haven't done that yet, but the scenario outlined in the question is definitely something to be concerned about.
Okay, thank you. And another question is, in slide 36, what is the guarantee that contraction or term
36.
is less than 1?
Okay. The hand wavy answer is everything needs to be small enough. Okay, so so mu is going to be the gradient dominance term. Eta, so eta is equal to, so this is the combination of the local step size, the global step size, and I believe the number of the number of iterations of the local algorithm you run. So in order to guarantee that this is less than 1, you need to ensure that the step size is sufficiently small.
Okay, thank you. And there are
I
several other
should say that
questions.
the details for sort of all the parameters, I'm also hiding what's in C1 and CU. The details are all in the paper.
Okay, okay. So there's a question asking, the central server is under whose control?
Right. Okay. So that's a really good question. In the so if I go even further back, the central server doesn't have to be under anyone's control. In the very first setup, sorry, I'm just scrolling back to right in the very first setup, this was just a separate entity, but you can change this. The server could be co-located with one of the devices. The only thing that's sort of important is that the data is not exchanged directly between clients, right? That's not allowed. But actually having the server, if I could put the server here, as long as the data isn't sort of doing that, then the server can be co-located. You can also have multiple servers, and the servers can be averaging, or some of the agents send to multiple servers, and then the servers average. There's a ton of complexity you can add in there. It just, as I say, it complicates the problem, but it probably provides more robustness.
Okay, thank you. And another question here is how to choose initial K before we proceed for optimization algorithm.
Yeah, that's a great question. And in sort of all of these settings, it's essential. So we actually have a paper. There is some Andy Lampersky and a few other people have papers on this. But essentially, you can do things like you can run like a discounted LQR cost for one of the systems to get a stabilizer just for a few iterations from simulation data. We're about to submit a paper where it tells you if the systems are all stable, it's much easier. We're about to put out the paper where we can do this for unstable systems in a sort of sample efficient manner. We refer to the literature in the paper, so I'm going to duck that question if you don't mind. But if you invite me back in a few months' time, I'll tell you exactly how to do it.
Okay, thank you. And another question is, what do the clients share? Models, data, or cost functions?
Great. Okay, great question. The clients, so in the federated averaging, let me get to, I'll get to the LQR version. The clients definitely don't share data, right? Sorry, just let me slide over. Right, okay. So what the clients share. The clients share the global controller, right? So initially this will be some stabilizing controller, but after every iteration, this global controller is updated. So the clients all share this controller. Beyond that, the clients don't share. Well, okay, that's also not true. The other thing the clients share is, so implicit in my zeroth order algorithm is that they can evaluate CI, right? And that is a function of the Q and the R matrix. And the Q and the R matrix in our setup, it's the same cost for the LQR problem. So if I come back to here, it's the same Q and the same R for every system. The A and the B differ, but the cost is the same. In the meta-learning case, the Q and the R per task are allowed to be different as well, right? Because the way we define the tasks, sorry for sliding around quite so much, the Q and the R are part of the tasks. So here, everything is different. But in terms of the LQR algorithm, they share very little. Right? The only things they share are the Q and the R So let me highlight in yellow. I've highlighted in yellow everything that is shared. And I should say, even the agents, we've written that the local update rule is the same for each agent, but it doesn't need to be. You can change that. It's just a little bit more math to then get the convergence. But this could be different as well.
Okay, okay. Are there any other questions? Okay, so we are running out of time. So thank you so much for Professor Anderson's great talk. And yeah, it's very interesting, very insightful.
Thank you for having me. This was a lot of fun.